Swayam Prabha, free DTH channel for education.
Hi students, welcome back to the online video lectures of the medical imaging course. In the last class we were concluding our discussions about image enhancements in the spatial domain. From this class onwards, for next few classes we will be discussing about image enhancements in the frequency domain. To this end, in this class we will start with an overview of complex numbers, a very quick overview, and it will be followed by a very basic level discussion about continuous time Fourier transforms. Okay, let's move on now to notebook mode. Let's start by discussing about complex numbers. How do we express a complex number? You all have used them in different courses like electrical circuits and also in signals and systems followed by DSP. So how do you represent a complex number? One typical representation is, let's call it as C, that's equal to A plus JB. This is the representation where you are using real and imaginary parts of a complex number. Now here J, this can be represented as square root of -1, and then if you want to write the real part of this complex number C, that will be equal to A, and then imaginary part of this complex number would be equal to B. So you have here on one axis real part, another axis imaginary part. This has a magnitude of A on the real axis and a magnitude of B on the imaginary axis. So this you could think of as your C. That's one way of representation. Now alternatively, if we want to represent this complex number in a magnitude phase form, that's also is possible. So how do you write that? Alternatively, C can also be expressed as C equal to magnitude be A, angle will be e power j5. That's how you represent this. This is also referred to as magnitude phase representation. Let's come back to again this diagram here. Now if you want to write here, for example, the magnitude of this would be given by A here, and this angle is denoted by 5. Let's try to also mention here the relationship between the real and imaginary part based representation and magnitude phase representations. Let us write down here the relationships between 1 and 2. Assume that you are given real and imaginary part representation shown in equation 1. Then in order to write it in the second way of representation, what would be your A value in terms of small a and small b? The magnitude A can be given by square root of a square plus b square. What about the phase value phi there? That's equal to tan inverse of b by a. Now assume that it's the other way around. You are given equation 2 and you want to write it in terms of equation 1. So in that case, what would be the value of A? You could again see from the diagram. It's equal to A cos phi, and B will be equal to A times sin phi. Next, why do we in the first place use these complex numbers? So the question is, why complex numbers? You could recollect from what you have done in your electrical circuits and networks while you are dealing with the phasors. Why have you moved from the normal scalar quantities to vector quantities? Suppose the parameter of your interest has two variables. Sometimes it is very convenient to handle particular vector as a complex number. So basically, one answer you could look at for this is describe a vector residing in a 2D plane. This is very convenient to describe a vector which is residing in a 2D plane. The same thing here, assume that you have a quantity which has, let's say, a and b, that's the vector. Now you could represent it as just a complex number. The multiplications, additions and other operations, and also of course there are many other reasons as well, becomes very convenient the moment you are representing them as a complex number. So for example, you were using the same in your electrical circuit course to represent the current. It has not only the magnitude but also phase. So the magnitude and phase of that you would be representing as a times j phi. So I hope you remember that. Suppose you have a current which has magnitude of I and then making an angle of phi with your reference plane. If you are representing it as I times e power j phi, then all your analysis becomes very convenient. That's one thing. And also then when it comes to your DSP course that you have done, e power j phi turn out to be the eigenvectors of an LTI system, right? So that's also where you are using it. Just we will recollect few points that would be essential for you while we move on to the analysis in the frequency domain, and also as we move on to analyzing the rotating magnetic fields in case of magnetic resonance imaging. So now I would just put certain scenarios and would ask you, how do we represent that in a complex form? Suppose you have a vector of magnitude a and assume that it is rotating in the xy plane with an angular frequency of omega, and it is rotating, let's say, in the clockwise direction. Then also assume that it has some starting phase phi. Now, as since this is varying with the time, you call this as c of t. Now given this, you pause your video and work out how you represent this vector in terms of a magnitude phase based complex number. Okay, so the magnitude is capital A and its initial phase is starting phase of phi. Okay, so A into e power j phi is your initially. You could notice here we are considering anti-clockwise as positive. For us this is positive, so obviously clockwise would be negative for us, and it is rotating at an angular frequency of omega over time. So this is how you would be representing it, e power minus j omega t, because it is rotating in the clockwise direction, right? So if you want to plot it here, a is this magnitude, this initial angle is phi, and it is then rotating here in the clockwise direction, and the rate is omega radians per second. This is your x plane, this is your y plane. You will come across later while we are discussing about magnetic resonance imaging acquisition that you have rotating magnetic fields whose projections you would be taking in xy plane, which would be varying. For representing them, you would be using these rotations. There, in fact, in addition to the magnetic field rotating at an angular frequency of omega, you will also have cases where the strength of this magnetic field also would be reducing exponentially. That also you should be able to represent using these complex numbers. Let me specify one such scenario here. Similar to the above one, you have a vector of initial magnitude c naught, a vector of initial magnitude c naught and initial phase phi naught. Assume that it is rotating with an angular frequency of omega in the clockwise direction. Okay, now what we said, additionally its magnitude is decaying exponentially. So we will write here with an exponentially decaying magnitude of, so let's call it as by a factor r subscript L. Then how do you represent this? Let's try to draw this out here. You have an xy plane. Initially it is having a magnitude of c naught and a phase of phi naught. It is then rotating in the clockwise direction, and while rotating its magnitude also should keep on reducing, and of course eventually becomes 0. So this would be rotating in this way and eventually over time becoming 0. So how do you write it in terms of an equation now? Let's call this as c of t. Initially it has a magnitude of c naught and phase is phi naught, e power j phi naught, and it is rotating at an angle of e power j omega t, and since it is rotating in the opposite direction, it should be, or in the clockwise direction, it should be e power minus j omega t, and then its magnitude is also reducing, so that should be just a real e power minus rl into t, and of course this rl here, since it is exponentially decaying, should be greater than 0, and that would give you the equation for a magnetic field, or you call it whatever it is, a vector you can simply call it, which is rotating at an angular frequency of omega in the clockwise direction. Notice the magnitude contributed by e power minus j omega t is always 1. It only contributes to the rotating field, where this so modifying only the phase information. And on the other hand, notice that this contributes only to the magnitude and nothing to do with your phase value. So this is your expression, which will be very handy for you later while we are discussing about rotating magnetic fields, projection of them onto xy planes. With that, now let me move on to an introduction to continuous time Fourier transform. Let's start our discussions from one-dimensional Fourier transforms. As you will notice shortly, the kind of definitions that we use in this medical image processing course would be slightly different from what you have already got used to in our DSP course. So what I would do is I'll start with the DSP course notations for this 1D Fourier transforms, and then I would write those notations which we would be following in this course. For this purpose, let me write it as DSP course notations. If you recollect, x of t be the one-dimensional signal there, for which we would like to compute the continuous time Fourier transform. We were using this notation of x of j omega. Now x of t can be represented as there will be a normalizing factor of 1 by 2 pi. There you have its Fourier transform x of j omega, where this omega is varying from minus infinity to plus infinity. This would give you the weight and complex exponentials of e power j omega t. You vary it over all values of frequencies. That was your x of t. Now the Fourier transform x of j omega, how do you represent that? Now you vary t value from minus infinity to plus infinity, x of t into, here you have e power minus j omega t dt. Now when it comes to the medical imaging course, I am going to modify these notations such that they would later fit nicely into MRI frequency domain acquisition of the signals. So that's why I would write here MI course notations. So this is a time domain signal we are writing. There it's a spatial domain signal. So instead of using it as x of t, we are going to call it as f of x. That's one difference. Then it is very common to refer to the frequency domain as kx and ky space when it comes to MR imaging. So what we would do here is this original signal we call it as f of x, and here whenever there is frequency we still use capital letter, but instead of calling it as omega we are going to call it as kx. And another modification we are going to do here is omega is radians per second, but it is quite common to use heads here in the frequency domain instead of this for MR imaging. So we would follow the same notation throughout our course. So what would happen then, take a look here. Your omega is essentially 2 pi. If I am using k for frequency, this is 2 pi kx. You do the change of variable in this equation. Then d omega equal to 2 pi into dkx. Then 2 pi, this one cancels out with 1 by 2 pi, right? So there is no more any factor of multiplication remaining there. So how could we write that now? Your f of x would be equal to, now instead of omega, you are calling it as kx, varying from minus infinity to plus infinity. F of kx multiplied by exponential of j times 2 pi k subscript x into x, derivative of k subscript x. That's just the simple change of variable we were doing here. Now let's write expression for f of kx. Now what is that you would vary? X is varying from minus infinity to plus infinity. F of x exponential of minus j 2 pi kx times x into dx. Now you all know this, that f of kx you would refer to as Fourier transform is the quite commonly we call it, or you also call it as frequency spectrum of f of x. To understand the properties that we are going to analyze shortly, you could have written this complex exponential f of kx in terms of real and imaginary parts also. So just let us write that as well here. All you need to do is e power minus j 2 pi kx times x, you write it as cos minus j sine and expand that. What will that give you? F of k subscript x is equal to, the real part would be x varying from minus infinity to plus infinity, f of x into cos of 2 pi k subscript x times x, that's your real part, and imaginary part will have minus j times, again here your x is varying from minus infinity to plus infinity, f of x into sine of 2 pi times kx into x. Of course you are integrating with respect to x, I should have kept dx here as well. That's the expression. Anyways, you have done a thorough analysis of it in your earlier courses, so what I would do here is I'll restrict myself to analyzing only few important properties here. The rest anyway, I request you to go back and refer to your earlier course notes for signals and systems as well as DSP. So one important property that I want you to pay your attention is what happens when your f of x is real. This is very important because most of the times your signals are real, okay, input signals to a system are real. So then what would happen? This is again, I am not going to derive this as you all have done it multiple times in your earlier courses. All I would say is f of minus kx equal to f conjugate of k subscript x. That means if you look at the Fourier spectrum, frequency spectrum of f of x, if you want to have its value at a negative frequency kx, if you take the value at positive frequency and take complex conjugate of that, then both of them will be equal. So this complex conjugate property is there when your f of x is real. Hope you also remember how this property is referred to as. We discussed in the DSP course already. This property is referred to as Hermitian symmetry, right? So in other words, it is enough for you to give only half of the spectrum, because the other half you get by simply taking complex conjugate of it and putting that value on the negative side. So if you want me to draw something here at k naught, if my value is going to be a plus jb at minus k naught, what would be the value here? This would be equal to, what is it that I am drawing here? Okay, this is my, let's say, kx here. What I am drawing here is f of kx subscript x. So this would be equal to a minus jb. So what can I say also then? My real part of f of kx, if you look at just the real part, it is same at k0 and minus k0. So this is an even function, is it not? Now, when it comes to the imaginary part, this is equivalent to an odd function, f of minus x equal to minus f of x. So imaginary part of f of kx, we are just stating it slightly differently. The above Hermitian symmetry property, that's all, is an odd function. Now let's take another special case where assume that if your f of x is strictly imaginary, if your f of x is strictly imaginary, then what would happen? It's very easy to analyze this. Anyway, I leave that part to you. I would directly write the result here. Your f of minus kx would be equivalent to minus of f conjugate of kx. Now given that your f of x is purely imaginary, then what would happen at k0? Let's say if you have a plus jb, what are you going to have the value at minus k0 is take conjugate. Okay, that means a minus jb, and then take negative sign to it. So then this would become minus a plus jb. This property is referred to as anti-Hermitian property. In other words, the real part of f of kx is an odd function now, and imaginary part of f of kx is an even function, right? So from now onwards we would follow these definitions of f of x and f of minus kx for the rest of this course. Now let's extend it to 2D. So let's write the 2D continuous time Fourier transform now. Two-dimensional CTFT is what we are going to write here, the definitions of it. Now it's a two-dimensional function, so instead of f of x, from now on I would be writing it as f of x comma y, and the continuous time Fourier transform we would refer to it as capital F of kx comma ky, the frequencies in the x and y directions. Now how do you write f of xy in terms of the other? F of xy equal to kx is varying from minus infinity to plus infinity. Similarly, your ky is also varying from minus infinity to plus infinity. You have here f of kx comma ky e power, here you will get plus j, right, when you are writing small f of xy. So e power j times 2 pi into kx into x plus ky into y. It is just like multiplying e power minus j 2 pi kx into x multiplied by e power j into 2 pi into ky into y. That's eventually we are summing up both the exponentials and putting them together. Now you are going to integrate them with respect to which variables? Integrate over kx and integrate over ky. Now let us write the expression for f of kx comma ky. What would be that equivalent to? Now you vary x from minus infinity to plus infinity. Similarly, y from minus infinity to plus infinity. Inside that you have f of x comma y exponential of e power minus j into 2 pi into kx into x plus ky into y, integrating with respect to x and integrating with respect to y. Okay, this is a very straightforward extension, as you could see here. Now I would give you as an exercise to solve some of the CTFTs for the one-dimensional cases. This would work as a more of a revision or warm-up of what you already know. So please do that by the time you come for the Zoom discussion class. So what we are going to see now are some examples, very important things. This you should know by heart. Examples of one-dimensional CTFTs. By the way, there are slightly different names that are used in case of the MRI domain. So I will introduce those naming conventions also here. The first one I want you to work out is box function. This is also referred to as rect function. The symbol that they use for this in 1D is rect symbol with X. This is how they indicate this. Okay. Now, how is it defined? It is there from -1/2 to +1/2 of X, and during that interval the value of this function is 1, and in all other places it is 0. So how do you define your rect function? F of x is your rect function, which is defined as it is 1 if your x value is in between -1/2 to +1/2 and 0 otherwise. So in your DSP course you have done for the notation where you are using omega. Now I want you to work it out for the kx notation. Okay, so frequency in hertz, that's what I want you to do. So for this, your first exercise is compute f of k subscript x. That's your first exercise. The second exercise, I give you sinc function. Now for this sinc of x, you compute the CTFT. What is that? So how did the sinc of x also, you know that we discussed earlier, there are two definitions of it. In physics, usually the sinc of x, we write it as sine of pi x by pi x. There is another notation people would follow to represent sine of pi x by pi x. They write it as sinc of pi x, but we will follow this notation, sine of pi x by pi x. For a quick reference for you, so this value at x equal to 0 is 1. This is going to become 0 at 1, 2, 3 and so on. Then magnitude will be decaying as you move on. So on the left hand side also is anyway symmetric. Only at integer values it is going to become 0. This is how the sinc of x would look like. So please find out what is the CTFT of sinc of x. Third one, delta x, what is the CTFT for it? Fourth one, you could use the properties to figure it out as well. 1, what is the CTFT of it? Then you have a shifted impulse delta of x minus x naught. What would be the CTFT of it? Now the next one, you are multiplying, let's say 1 with complex exponential. So then what would be the CTFT of it? Then you take cosines and sines. These are also very important. You will come across them. Cosine of 2 pi times k naught x. What is the CTFT of it? What would you do here? You write it as e power j plus e power minus j and use the sixth property to do that. Similarly, do it for sine of 2 pi k naught x. What is the CTFT of it? Then the ninth one, you know it already by the name impulse train. There are other names that are also used for it. For example, they call it as Dirac comb. Yeah, of course, this is also known as sampling function and also known as Shah function. And the symbol used for it is this, for the Shah function. And there is also another symbol that the people typically use for it is to show it as impulse train delta of x. So how does it look like? With a periodicity of 1 we are going to consider. Let's say it is at 0, 1 impulse, 1, 2, the periodicity of 1 is here, then -1, -2, so this would continue. This is the impulse train you have. This is your x and this is your impulse train Shah function of x. So compute for this, what is the CTFT of it? Okay, and the last one for you is e power minus pi x square. Why I have given you this particular function will become clear as we move on. particularly to 2D CTFT, but before that I would like you to compute what would be the CTFT of e power minus pi x square. I'd give you the answer also. You try yourself to find it out. Answer will be e power minus pi k subscript x square. Try to derive on your own. If you cannot do that, try to find it out from some source in the net, but have the derivation for you. Okay, by the time you come to the next class, come prepared with all the derivations for all these 10 cases. Okay, I'll stop here for now and we'll continue our discussion in the next video lecture. Thanks for watching. See you in the next video lecture. Bye. Take care.